So today we're going to be looking at a theorem involving eigenvectors and eigenvalues, and we'll see that eigenvectors corresponding to distinct eigenvalues are linearly independent. So here's our first theorem. If T is a transformation and V1 through Vn are eigenvectors with eigenvalues lambda 1 through lambda n, and those lambdas are different, so lambda I is different from lambda j for j not equal to I, then the eigenvectors are linearly independent. Okay, let's take a look at the proof. This probably doesn't surprise you. We're going to do a proof by induction on n being the number of eigenvectors or the number of eigenvalues. Case n equals 1. Inductions usually start with a base case. In this case, we'll look at n equals 1. If you think about it, that's trivial. I leave the details to you. Now let's look at the inductive case. So we're going to assume the statement of the theorem is true for any set of n-1 or fewer vectors. If that statement confuses you, this would be a good time to review mathematical induction. So we're going to assume the statement of the theorem is true for any set of n-1 or fewer vectors, and our goal is to show the statement of the theorem is true for any set of n vectors. Okay, so we want to show that V1 through Vn are linearly independent, so we start with a linear combination, C1 V1 plus all the way up to Cn Vn, set it equal to 0. And remember, our goal is going to be to show that C1 through Cn are all 0. So what we do is we apply the transformation T minus lambda n. So we applied T minus lambda n to that linear combination of V1 through Vn. Now, since TVI is lambda I Vi, because Vi is an eigenvector with eigenvalue lambda I, TV1 is lambda 1 V1, all the way up to TVn is lambda Vn. Now, you'll notice T minus lambda n Vn is 0. Okay, we now use the inductive hypothesis. V1 through Vn minus 1 are linearly independent. I'm just going to scroll now. Blah, 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 blah. Blah, blah. Obviously, then, Cn is 0 as well. So we've proven C1 through Cn are all 0, and we're done. Now let's review this proof. So first note, it's by induction. And recall the trivial case, or I should say the base case, was trivial. So moving right to the inductive case, we want to assume the statement of the theorem is true for any set of n-1 or fewer vectors. Okay, we did a little work, but the key step is applying the transformation T minus lambda n to our linear combination. The rest of it is just a little algebra and a little checking. We did a little work. We got some linear combination of V1 through Vn minus 1 being 0. But V1 through Vn minus 1, we can assume are linearly independent by our inductive hypothesis. So our coefficients are 0. And the only thing we have left in our linear combination then is lambda n Vn. So lambda n Vn is 0, so Cn is 0 as well. So notice we have all of the C being 0, and that suffices to prove that V1 through Vn are linearly independent. So now we've shown that blah, 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 blah. In the next lecture, we'll consider blah, 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 blah. Okay, done.